I'd like to switch to Shreyas Sen, professor of, assistant professor of electrical and computer engineering at Purdue. Clearly that is sort of the next step in a point-of-care system is the electrical engineering, and it's only become more and more imperative as we move to these personal electronic devices and such a higher density of information. So please welcome Professor Sen. We can't hear you.
Thank you, Michael, for the quick introduction. After my PhD from Georgia Tech, I was at Intel Research for 4.5 years, where I contributed to communication circuits, including impacting USB-C type. For last 4.5 years, I have been at Purdue, where I have been looking at communication around the human body and sensing to build very well-connected point-of-care devices and other electronic devices. So to that end, let me figure out the movement. So to that end, we all know that the wearable point-of-care space is increasing. There are many cool sensors that are being built. One such example is this year, in collaboration with Professor Chi-Wan Lee and with a big team from Purdue, we published in Science Advances a sensor which can detect swallowing. So this is a flexible sensor which detects the EMG, as well as there is a strain gauge which can detect strain. Our part, being an electronics design group, was this white box, which then converts this information and, as you see over here in the red, transmits it through Bluetooth. So it was very convenient for this project to carry around this device over here. But in future, as you have, as Michael pointed out, many sources of information, both in the same sensor as well as at different sensors around the body, having such a device may not be the most efficient way. So to that end, I'm here to tell you, this is the present, but the future should not look like this. In the future, we should be able to take this, miniaturize it down to a small dust-sized particle in the sensors themselves. And why we want to do that? Because at the end of the day, the adoption depends on the usability. If you have to carry 5 of these big boxes on your body, you're not going to use it. Second, we are going to deal with a lot of private data, including, for example, accessing our pacemaker, which needs to be very secure. People should not be able to snoop into these networks and tamper with your body. Third is, we already see this fatigue of charging these electronic devices. We all have like 4 or 5 devices already. If you have 5 more devices on your body, are you going to take these off and charge every night? Or even like twice a day? So it needs, the ideal goal is to go towards perpetual life for these devices. It should not have harmful chemicals. And talking about today's battery, we know those have harmful chemicals. So can we get rid of battery for these kind of connected point-of-care devices? And eventually, all of this should lead to huge amount of health data, which multiplies from different sensors, giving very meaningful insights. So how can we get there? So in today's talk, I'll show you the biggest challenges and some significant improvements in recent times to those challenges. So if you imagine this kind of a sensor node would have first the transducer, what I call is the material that is converting your biological signals to some kind of electrical signal. And then the circuitry. The circuitry has sensing circuitry, some kind of a computation on board, and then the communication. Now, if you try to look at the energy background between these 3 parts, specifically focusing on the computation and the communication, in this chart, what you see on the x-axis is number of bits switched or number of bits communicated. And on the y-axis, you see the energy. And the lower lines are basically theoretical limits in both cases, in the blue and the red. Blue being the computation energy and the red being the communication energy. And the higher lines are more practical limits. You can see more details in our paper, but you can see that typically the communication energy is 4 orders of magnitude higher than the computation energy. What does it tell us? It tells us if you get information, if you get data about our body on a sensor and trying to send that data, your energy non-optimal. You should do compute on that data right at that location to extract information out of that data. Go from data domain to information domain because computation energy is so cheaper compared to communication. That's the first insight. The second insight is come up with technology which should reduce this communication energy and make it more meaningful, more comparable to the computing. It's not going to happen ever because there is the fundamental limits, but bring it down. So I'll show you efforts in both directions. So in summary, the pain points in today's point of care wearable medical sensors is the biggest one is communication. Today's Bluetooth is like 10 milliwatt, and we need to get it to the microwatt range. Sensing is already almost there. You can do this. Our physiological signals are generally low speed. So you can do this low speed sensing at tens of microwatts today, and there is already path towards going to sub microwatt. And then bringing the intelligence to go from the data domain to the information domain is what we call it in-sensor analytics or in-sensor intelligence, which then helps us send less amount of data. We just send the information, reducing the energy. So for future energy autonomous or battery-free nodes, we basically need at least 10x improvement in the communication side to make this feasible. And also we need a lot of improvement in the integration technology. Some of the technologies are already there, but we have to integrate these transducers with this maybe silicon or non-silicon integrated circuits to have a very wearable kind of a form or even implantable form factor design. So the next part of the talk, I'm going to tell you how we have addressed the biggest bottleneck in these connected wearable medical devices that take the connectivity energy from tens of milliwatts to sub microwatt through inventions at Purdue in the last 4 years. But before I do that, let me paint a picture of how the future is going to look like. Around our body, there are going to be many consumer electronic devices, as you can see on the left, as well as many medical devices, as you can see on the right. And these devices are going to form a subset of the Internet of Things or IoT, as we know. And they're going to have a common distinguishing feature that all of them are on or in your body. So they have a common medium that is your body. And hence, there is a new term that is emerging, Internet of Body. So these medical and consumer devices are going to be part of this network called Internet of Body or IOB. I'm going to show you how to make it secure and efficient. The first question is, are these IOBs secure today? To understand that, let's understand what goes on. When we send something in a sensor, we typically use electromagnetic fields and radiate the signal out in all directions using an antenna. And the information goes all around us. If for Bluetooth 30 feet, for Wi-Fi could be even more. And anybody in that vicinity can snoop your signal and can hack into this network with some hacking techniques. Imagine you are sitting in a coffee shop and trying to connect your pacemaker to your watch. The electromagnetic signal that you send out goes throughout the coffee shop, and anybody in the coffee shop has access to it, access to the physical signals. We try to encrypt this using encryption and passwords, but passwords also gets hacked, and there is a significant vulnerability because everybody has your signal. Now, this fear propelled US Vice President Dick Cheney to ask his doctors back in 2011 to stop all communication to his connected pacemaker, because he was influenced by the Broken Hearts episode of the Homeland TV series, actually in the 2012 timeframe, where it was shown that somebody hacked into the vice president's pacemaker and killed him. But are these only stories? In the same time frame, famous hacker Barnaby Jack actually demonstrated in front of a big audience at conferences live that he can break into connected pacemakers and insulin pumps, making this vulnerability real. And as soon as, even recently as last year, many government agencies has come out with these kind of vulnerabilities, which has led to recalls of name brand companies. What can we do about it? So, like I said, in this Internet of Body, all of these devices are on your body. And our body has a lot of water, so it's kind of conductive. So why not use the body's conductivity to use the body as a wire and send signals through it? Inject small amounts of electrical signals which are 10,000x below the safety limits or 1,000x below the safety limits, and then pick it up other locations on the body. What happens in that case is these signals don't come outside of your body, and any nearby attacker cannot snoop these signals. Also, because the signal energy gets contained within the body, these are much more efficient, as I will show later. So we published this concept in Nature Scientific Reports last year, where you can see the lady on the right using a Bluetooth. Her signals goes up to actually much more than 5 meters, up to 30 feet. Whereas the boy on the left is connecting his watch to pacemaker using the body as a wire, and the signals cannot be picked up any more than 1 centimeter off of the body surface in these frequencies. This opens up a new field of connectivity for wearable devices. And let me try to paint from a very high level why that is possible. On the x-axis, what you see is frequency. So this is the megahertz range and this is gigahertz range. And this is today's systems. On the gigahertz range, 2.4 gigahertz, as you might know, is Bluetooth. We use this electromagnetic spectrum. And with today's technology at lower frequencies, which is called the electroquasistatics, the signal is very low, so it is not usable. Using our patented technology, we have come up with a technique such that the loss in these low frequencies have improved by 100x, making it usable for the first time. Now, you can use this physically secure range, or in other words, body as a wire, to do a lot of connectivity around the body, both securely as well as efficiently. We demonstrated this with an integrated circuit that we built. So you can see the size of the integrated circuit, it's like tiny. And that's the world's lowest energy body area network, or IOB in IC. We benchmarked it as a function of data rate and total power. You can see compared to the wireless body area network like Bluetooth, this is 100x lower energy. And compared to other state of the art, it is 18x lower energy. But for that was a higher speed system. For the physiological signal monitoring or wearable point of care, we don't necessarily need that high speeds. So we built a second chip just this year, where we have demonstrated this is Bluetooth in the milliwatt range, previous work in 40 microwatt range, and we have only 415 nanowatt. So this is the first sub-microwatt communication for wearable devices around the body, which now means you can harvest energy in the level of, from even movement, microwatts. So your communication can be battery free, which was never possible before. So this fact that electroquasistatic human body communication is physically secure was widely picked up by the news sites, as you can see here. Somebody said scientists design a network that lives inside your body. Others mentioned that it demonstrates a huge leap in medical data security, which may affect many bioelectronic medicine for years to come. This was recognized by the MIT Tier 35 India Award, as well as CNBC TV interviews and a TEDx talk in Indianapolis last year. So we have demonstrated these devices that it works. And last year, like I pointed out, US Department of Homeland Security had come up with a vulnerability in the radio communication for the security reasons I mentioned. And following that, IEEE Spectrum basically pointed out that, oh, these vulnerabilities exist for medical device communication. And there is this new technology from Purdue using the body as a wire. Why not just use that? So I want to leave you with that question, that while the devices are on your body, why not use the body as the communication medium to get much more security and efficiency to change our wearable point of care connectivity. I'll stop here.
Thank you. I find this deeply fascinating because, you know, we were promised as a society to control our electronic and medical records, and today, you know, it's everybody and their brother has a business that's controlling our access to data. Our data is not being used, and there's many papers that show if they just looked at the data that they already collected, it would help our health outcomes. So the idea that the body could, you know, individually store our complete medical data record is amazing. So I guess my question to you is, you know, the barriers to entry. When you're going to this kind of scale of changing the paradigm, you know, you've got a lot of people that don't want to see it change.
Yeah, so the change will be slow, as in any technology, and we have to find early adopters. And the early medical space may or may not be the early adopters because medical space needs longer time frame. It can be used for other applications like opening doors, which could be a completely different application of this technology to start the adoption. And then as people see the benefit and it works, I hope in future, and I'll dedicate my life toward that, that it changes the paradigm of body area network connectivity for even medical devices.
Thank you.